Hello everyone and welcome back to Analog Electronics Lectures. In today's lecture, we'll talk about several configurations for operational amplifier. We'll see how the operational amplifier can be working as an integrator or as a differentiator, and also we'll see many different configurations that can be built in order to make several operations for the circuit. Okay, before going to analyze some circuits, let's come back to the basics of the current and voltage inside some passive elements, which are let's say, for example, the capacitor. Here we have a capacitor. Let's say that there is a current flowing inside this capacitor, and this current is called IC. So by definition, the current here, IC, equals to the capacitor value, the capacitance value, times the first derivative of the voltage applied on this capacitor, C times dV by dt. You will need this definition when we go and calculate the voltage, output voltage and input voltage of of some configurations of the circuit, such as the integrator and the differentiator. Okay, so this capacitor thing will be useful for the integrator and the differentiator circuit of the operational amplifier. Also, if we have, for example, a network like this, we have three resistors, let's say, resistor 1 and resistor 2, R1, R2, and R3. And there is a current flowing in these resistors in this way. So all of them are pointing to this point, to this node. So this is I1, I2, and I3. The sum of these currents, I1 plus I2 plus I3, is equal to 0. Okay, and this is what we call the Kirchhoff's current law. Okay, and here, for example, we can say that I1 plus I2 is equal to minus I3, and so on. So this is the other one. So these things are important in order to analyze some circuits of the operational amplifier. Let's go and find the first circuit of the operational amplifier. Let's have a look at this amplifier. Here we have an operational amplifier, inverting, non-inverting. And here we have a resistor. And here we have another resistor. And this input is connected to ground. And the non-inverting input is connected to V input. Okay, this is the input voltage here. And we said this is V plus, this is V minus. And here, I'll say this is R. The difference here is that this resistor is the load resistor. It's not a feedback resistor, although it's connected from the output to the input, but this will be measuring the output current. Okay, so this is a load resistor. Okay, I will say this is I out. Okay, and here is I1. Now, using the voltage rule of the operation amplifier, we said that V minus equals to V plus, and all of these equals to V input. Why? Because this node and this node are same, and V plus is connected to V input. Okay? Now I1, if you try to calculate I1 here is how much? The current here. This node, this voltage, V minus 0 over R. So V minus over R. Okay? And V minus is how much? From this definition, it's V input over R. Okay? So here finally, we can say that I out equals to how much? This current I out equals to I in, because we said in using current rule, the current here is 0. So I out is equal to I1, and this equals to V in over R. Okay, altogether here we can say that I out equals to V in over R. And this circuit actually is what we call voltage to current converter. Here we enter a voltage here, we have voltage on the input, and finally we get current on the output. Why the current? Because this is a load. Okay, now before going to the next circuit, let's revise the non-inverting amplifier. You have feedback resistor RF, and here we have resistor connected to ground, and this is connected to the input, and the input is taken from here. Okay, this is V plus, V minus, and V out. Okay, now I have one question for you. How this is, we said what? Non-inverting operational amplifier circuit. Okay, and we know that V out over V in equals to how much? R feedback plus R over R, right? Okay, the question is how to convert this circuit, the non-inverting amplifier circuit, to an inverting amplifier circuit using one move only. We need to make some changes here. One change only, one move. We need to replace something with another thing and convert this circuit, this amplifier, to be from a non-inverting amplifier to inverting amplifier. What should we do? Now, think about it. If we replace this ground with this input, so we put the input here, okay, and put the ground here, okay, what happens to the circuit? It will be a typical inverting amplifier circuit, okay? So here, what is the inverting amplifier circuit? Like this. The non-inverting is connected to ground, and this feedback resistor is here, RF, and this is connected to V minus, right? And this node, which is here, okay, connected to another resistor, which is R, and this all connected to V in, and here V out. So V out here over V in equals to how much? Minus R feedback over R. Okay, and just these are just typical circuits, same circuit. We just change what the input with the ground, and that's it. We got different configuration for the circuit. Let's move to the differential amplifier circuit, or what we call the subtractor. The subtractor actually is a differential amplifier circuit. Here we have OpAmp with a feedback resistor, and again exactly similar to what? To the inverting amplifier, and this is connected to the input voltage. Here we have R1, and here we have R2. Now, because this is a subtractor, so instead of connecting this non-inverting input to a ground, what we do, we just connect another voltage divider here, resistor, and here we have another resistor. By this way, we have two inputs, and here we have ground connected to this resistor. So I'll say this is R2, this is another R2, let's say it's the same value, and this is R1. Okay, now let's label these values here, V1, V1, and V2, and this is V out. Okay, of course it is V minus, V plus. Now let's try to find the gain of this amplifier. From the voltage rule, we said that V minus V minus here minus V2, this value, equals to how much? It's a voltage divider. So the voltage applied on this resistor, okay, equals to how much? R2 over R1 plus R2 times V out minus V2. Where is V out minus V2? The voltage applied on the whole branch here. Okay, V out minus V2. Clear? Okay, from this equation we can say that V minus equals to R2 over R1 plus R2 times V out minus V2 all plus V2. Okay, now V plus equals to how much? V plus again from this equals to how much? R1 over R1 plus R2 times V1. So V plus, the voltage here, is equal to how much? R1 over R1 plus R2 times the whole voltage, which is V1. Okay? From the voltage rule, since we have V plus equals to V minus, here, this is just a typical circuit connected to a feedback resistors. So this value here must be equal to this value. So let's equalize them and find the relation. So we can say that R2 over R1 plus R2 times V out minus V2 plus V2 equals to R1 over R1 plus R2 times V1. Let's continue to the next page. So here R2 over R1 plus R2 times V out minus V2 plus V2 times, we can multiply here R1 plus R2 and here R1 plus R2. This means 1, but we need to unite these denominators. Okay, so this will be what? R1 over R1 plus R2 times V1. Now we can easily remove these, this with this with this. So R2 times V out minus V2 plus V2 times R1 plus R2 equals to R1 times V1. Just distribute this, the R2 V out minus R2 V2 plus R1 V2 plus R2 V2 equals to R1 V1. Okay, R1 V2 and R2 V2 with R2 V2, these will go together. Then we have R1 V1 and R1 V1, and here we have R2 V out, right? So we can say that R2 V out plus V2 R1 equals to R1 V1. Okay, so here R2 V out equals to R1 V1 minus R1 V2. Okay, and this will be here R2 V out equals to how much? R1 times V1 minus V2. Finally, V out equals to R1 over R2 times V1 minus V2. And this is subtractor, right? So this is the final equation. So we can say that V out equals to R1, which is the feedback resistor, and R2 is the input resistor, and V1 and V2 are the inputs. Okay, and this is a subtractor. So you can design a subtractor circuit using different resistors and different values of the input and get what? The output value. Okay, that's everything for today, and see you next time.